Yeah, so original title was Challenges in Disk-Planet Interaction. So I changed it a bit after seeing who else was going to talk about disk-planet interactions. And there was so many interesting talks about the physics challenges that we face. So I thought I'd focus on one particular challenge that is related to more of the computational aspects. And it's been alluded to several times already today. It is the very simple question of, well, how on earth do we get enough resolution in our simulation to resolve all the important scales? So I'm gonna. Oh, it's not my. All right. So I'm gonna first. What I'm gonna do is first introduce, well, the very basic setup that I'm interested in. So it's all with disk-planet interactions in mind. So define some of the important scales. Some of those have been talked about a lot already. And very importantly, well, which of these scales talk to each other? Which scales do we need to resolve to get reliable answers on the questions like migration and accretion that we're interested in? And of course, we'll very quickly establish that having a large simulation of a disk at a single resolution is not going to cut it. That's going to be way too expensive. So we need resolution that varies across the domain. There's various techniques for doing that, but some of them don't work very well for our purposes. We're interested in planets and disks, so hence my interest over the past couple of years in unstructured meshes, and I'll explain why. So once we've established that unstructured meshes are useful tools, we need to do some hydrodynamics on it. There's various choices you can make there as well, and I'll motivate some of the choices, some of my interests there. And finally, come back to the problem at hand. So how can we apply this to planets and disks? But first of all, the very basic problem that's been discussed extensively already. So we have a planet of a size, our planet, perhaps Jupiter. Jupiter size, if it's a Jupiter size, it might have a solid core of a certain radius as well. And of course, it's embedded in a gaseous disk. So the physics we need as a bare minimum is we need to do some hydrodynamics. For the purposes of this talk, I'm going to assume a very simple equation of state, mostly isothermal, although I think one of the challenges in physics is to improve on this, do some proper thermodynamics, as was shown already. And on top of that, we, of course, need the gravity from the star planet and ideally the disk as well. So some of the scales we might want to resolve. So the largest scale is clearly the disk size, which can be hundreds of AU big. Now the disks are, as well known, usually thin. So small aspect ratio, we take an aspect ratio of 0.05 at 1 AU, then the vertical scale of the disk is much smaller. If we put in a planet that is of a physical size of Jupiter, there's a factor of 100 smaller again. And if this has a solid core of roughly an Earth size of the Earth, we go another factor of 10. In between those important scales, such as the Hill radius of the planets, which for Jupiter is comparable to the scale height. The physical size of Jupiter is much smaller than the Hill radius. There's of course the Bondi radius we have heard a lot about. But if it turns out we really need to resolve all these scales, we're in a bad position, because then the dynamic range in our simulation will have to be about 1 million. And it's important to realize that if we start to introduce new physics like thermodynamics, magnetic fields, dust, these may introduce new scales that may or may not have to be resolved, but this is kind of the bare minimum, I think. So let's look at planet migration. So as been said already many times, so as we know, if we embed a planet in a disk, it launches waves at its Lindblad resonances, and these waves carry angular momentum. If they dissipate their angular momentum, they torque the disk, and the back reaction leads to planet migration. And this is, if we consider only these waves, that is about as clear a case of classic type 1 migration as you can get. If we want to calculate torques, calculate migration rates, what is the length that needs to be resolved for these waves is roughly the scale height. scale height h. So it's not too bad. If we want to do the co-rotation torque, so the torques from material on horseshoe orbits very close to the planet, that's more challenging because this co-rotation region can be smaller than h for Earth-like planets, but it's not necessarily much smaller than h for planets of interest if we an Earth mass or bigger. So I would argue that simulations like this, the resolution required in a global simulation, you need a couple of hundred of points, grid points in every direction, and that's challenging but doable. Challenging also because they have to be run for many dynamical times in some cases, but it's doable. Things get worse if you try to look into some of the details, in particular in disks of very low viscosity. So this is a problem that was already mentioned by Sijme-Jan as well. So if you have a low mass planet like an Earth mass planet, so the waves launched are linear, but especially in a low viscosity disk, if the wave propagates, it may shock after traveling some distance in the disk. This was of course shown in 2001 for the first time. And the results of this can be very interesting. You may get gap formation there. There's maybe a feedback on migration. If you want to do a numerical simulation of this turns out to be incredibly difficult. So the reason is that this wave propagates in a linear. This is linear at first. It propagates, and it needs to propagate without any significant numerical dissipation before it actually shocks and deposits its angular momentum. And this wave will be sheared by the Keplerian flow, and this is numerically very difficult. So on the left, I show a simulation from back in 2011 by Ruben Dong and others. So this is a vortensity plot, actually. So you see the wake. So the planet is somewhere here. This is the wake. This is its linear phase, and then at some distance from the planet, it shocks. There you get this vortensity change because this material has been shocked. What they found is that in order to capture this, this is a local simulation, I should stress, so a shearing sheet simulation, you need to resolve the scale height by roughly, well, more than 200 grid points. Now, of course, if you want to say something about migration and gap formation, you need a global run. So the resolution you require if you do that is a single resolution, 10,000, 30,000 grid points in every direction. So this is becoming quickly very, very large simulations. A second example that I'm interested in is more of an accretion problem. It's similar to what Chris and Judith had talked about already. So very simple setup again. So a planet consisting of a solid core. You do an isothermal, self-gravitating gaseous envelope. And as is well known, there exists a critical core mass beyond which there's no hydrostatic solutions for the envelope that connect to a disk. And of course, there's very famous 1D models like the one of Pollack et al. 96, but they have complicated realistic equations of state. There's a lot of thermodynamics in there. You can do it for an isothermal disk as well, as shown by Pechnik and Wuchtel back in 2005. And these are 1D spherically symmetric models. So if you don't have any hydrostatic solutions anymore, you might think, well, then this is when rapid gas accretion set in. But at that point, probably, it's maybe, as Sijme-Jan was mentioning, the gas accretion might be limited by the global disk supply. So we need a global disk, and we need an accreting core. Situation may be worse, as Chris was showing. So if subcritical cores that don't attract a lot of gas also know they're in a disk because of the flow close to the planet is dictated by the fact they're in a disk, then we're in big trouble, because then we need to resolve both the global disk and this core. So then we're in the worst situation possible, where this dynamic range of 1 million. So you can just quickly, what are the critical core masses? So if you do a simple isothermal self-gravitating envelope, you can for every combination of core mass, there's core mass and earth masses, you can choose a density at the surface of the core, and for every combination of core mass and central density, you can calculate a hydrostatic envelope. But the problem comes when you want to connect this to a disk. So the usual approach is, well, this planet connects to a disk at its halosphere, and this solid contour gives you the solutions that can connect to a minimum mass solar nebula at 5 AU, I think. So, and then you see, well, although hydrostatic solutions exist here, they can never connect to the disk at the right location. So you get a critical core mass here, which is much smaller than an Earth mass. So, very importantly, this depends very heavily on the thermodynamics. So this is an isothermal disk with a very small critical core, but typically you're talking about Earth masses. So we're in this, if we need to resolve this, we really need, if it's a simulation of a single resolution, you're talking about millions times a million grid points, so clearly crazy undoable. But of course, this is not a new problem. It's been around, I guess, ever since people were doing hydrodynamic simulations, and there's techniques of trying to vary the resolution with spatial location. These have been around for a long time. So the basic idea is, well, we can have large grid cells where we don't need resolution. If we need to refine the mesh, then we split one big grid cell in 2D into 4 grid cells. We need higher resolution, we split it again and again and again. So you get jumps in factors of 2 in resolution. So this is a typical refined grid where we need high resolution here, but very importantly, you can be very efficient in putting resolution only where it's needed. But you get these, what you can call topological defects in the mesh, where this grid point has one neighbor in each direction, but here it suddenly has 2 neighbors. So you need to do something special at these locations, and these are wherever there's a jump in resolution. That can be a very bad idea in some cases. So in a lot of cases it works very well, but in some cases it can be problematic. So in particular, when we're talking about this problem with a planet wake, which may shock. So obviously we want to refine at the location of the wake, where we want high resolution. So at this point, of course, the disk flow is supersonic, so it comes from the top in this case. So information propagates downward only. So what you get is there's a flow in this grid cell. It encounters this topological defect where you have to split it in 2. So but there's some freedom in doing this. So first of all, you want to be conservative. You want to conserve mass across this boundary, angular momentum, etc. But because you're splitting 1 into 2, there's some freedom in how you choose the contributions from one grid cell to the other. So that's usually not a problem. The bigger problem is on the other side, when again, still it's supersonic flow, the wake is gone, we want to coarsen the mesh because the resolution is no longer necessary, but now I have 2 cells that I have to combine into 1. If again we want to conserve mass, we want to conserve angular momentum, there's only one way to do it, you have to add these 2 up. But that can be a problem in a Keplerian disk, because if you take, for example, the Keplerian velocity, if I take the Keplerian velocity at this radial location, I average the 2, I do not get the Keplerian velocity at this location because it's nonlinear. So even in an unperturbed disk, you make an error here, which is first order in the size of the grid cells. So the result is that at this location you get pressure waves that are purely numerical, and that kind of sometimes they're not a problem. They're not big. You can try, well, let's make the biggest grid cells as small as possible. So there's ways of minimizing this effect. But for the particular case where you're interested in very small differences, very weak shocks, and their effect on the flow, this is really unwanted. So for the second example, if we think back to the planet envelope that we want to resolve, one thing you might try is, well, if the whole envelope is about the size of the scale height of the disk, the pressure scale height of the disk, you might think, well, let's embed a 1,000 by 1,000 by 1,000 mesh, which is the whole envelope, refined so that we can resolve the core. But so that's just challenging in itself to do for a long time. But this then still has to be embedded in a global simulation. So that has become very computationally demanding. So you might try, well, we don't need to refine the whole envelope because the core is somewhere in the middle. We only need this resolution here. The rest of the core, the rest of the envelope may not need that resolution. So you get a change in resolution across the envelope. But that sounds dangerous to me because this envelope is spherical, and then you're putting this grid of varying resolutions. I would be very worried about maintaining exact hydrostatic equilibrium in this case. But there's ways around this. So one way is, well, to go, especially in this last problem I mentioned, well, let's just make the method we're using to solving the equations high enough order so that this is not a problem anymore. So there's one way of going about it. Another way is, well, let's get rid of the mesh altogether. Let's do SPH, and this is an example of a simulation by Ben Aliff and Matthew Bate in 2010, where they did a local SPH simulation where they actually resolved the core of a giant planet. So this was actually published in 2010, and I remember speaking to Matthew Bate in 2015 where he told me, well, this simulation is actually still running. So that's because this is computationally very very difficult to do, even in a local setup. But so the way I've gone about it over the past couple of years, well, let's not get rid completely of the mesh, but let's choose a more flexible mesh. So this is a unstructured triangular mesh. So let's get rid of the square grid cells and work with triangles instead. So this is a zoom sequence on a unstructured grid at varying resolutions, so smaller triangles over here. And the thing to notice is that although the resolution varies by an order of magnitude in this particular example, there's no topological defects in this mesh. Every triangle is surrounded by 3 other triangles, no matter where you are in this mesh. So that's a big advantage, I think. So you don't need to do anything special when the resolution changes. Another interesting thing you can do, well, you can be very flexible in having internal and external boundaries. So that can be advantage. I'll show an example later, but when we think about embedding planets in disks as well. So this is a computation of a calculation of flow around a cylinder. So this is 2D. I've cut out, so it's a rectangular domain, but I've cut out a circle and reflecting boundaries here and flow around a cylinder. One other advantage, I'll come back to this later as well, is that the diffusion, numerical diffusion in such a mesh is much more isotropic. Because if you have a rectangular mesh, obviously you have 2 very special directions. If you do x, y, Cartesian, x and y are special. In an unstructured mesh, there's no such thing. There's no preferential direction. And another thing that is very useful is that these are Delaunay triangulations, and you can actually guarantee, at least in 2D, you can guarantee the quality. And by quality, I mean the shape of the triangle. So if you're thinking about rectangular meshes, you want your grid cells to be of equal size in each direction, ideally, to get comparable numerical diffusion in all directions. And you can, with these triangular meshes, you can guarantee that this is the case. So good quality triangles, which is very useful. Now, of course, the use of unstructured meshes have become very popular over the years, ever since, in particular due to the moving mesh crowd. which use Voronoi meshes, which is it's the dual of Delaunay. So it's not a it's essentially the same. So arguably started with the repo code. There's now many more. The rich shadow facts, which is a code I learned about. This is actually a visualization of shadow facts I didn't know about before preparing this talk. There's also, of course, Gizmo, which can operate in this mode as well, although it's basically meshless. So what they do is they try to combine some of the advantages of SPH, so the Lagrangian nature to get resolution at mass concentrations, but do the hydrodynamics on a mesh. So I'm not a big fan of the Lagrangian nature of these methods, because you distort by moving the mesh points around. You distort the mesh, and that kind of reduces the quality of your triangulation or your tessellation. So you have to counter for that in some way. But I don't think this is a too useful for us for the problems we're interested in disks. So once we establish, well, we can unstructured meshes are interesting for the problems where to get high resolution at very high resolution at very small, limited small areas in our computational domain. So we need to do some hydrodynamics on it. So there's, again, different choices you can make. So I think most of the moving mesh crowd have gone for finite volume methods, where you just, well, we have a mesh of Voronoi cells. This cell has neighboring cells, and we can solve Riemann problems on all sides to calculate what the interaction between those two is. But of course, in an unstructured mesh, some of the results that were derived for structured or rectangular meshes don't hold anymore. In particular, there's of course no dimensional splitting possible, because, well, which dimension? There's no preferential directions anymore. And also, there's no version, as far as I know, of the corner transport upwind method. So what you can do in an unsplit method to do a multidimensional integration. So if you do this kind of thing on a rectangular mesh, this is well known to be only first order correct, because you don't account for the multidimensional integration. You neglect some cross derivatives. But as is empirically known, the errors are usually quite small. I've yet to come across a problem where doing actual strength splitting makes a big difference to the solution. But we can do better, in fact, by using what are called nowadays residual distribution methods. So they used to be called fluctuation splitting methods in the 80s. So what you do is, well, you say, well, I'll define a residual, which is just the integration of the divergence of the flux term. So this clearly governs the time evolution of the state. So if the residual is 0, there should be no time evolution. It's all in equilibrium. But if it's non-zero, what we can do, well, we calculate the residual, and then we distribute this to the nodes of the triangle. So we do this for every triangle, and the final update is, so for every node we collect from all the triangles the residuals that were sent to this node, and that's the update of our solution. So of course all the magic is in this part. So how do we choose this? So there's various design criteria you can come up with. Well, of course you want it to be conservative, conserve mass, momentum, everything. So these three have to add up to the total residual. But a very important design criteria is, well, we can take into account the multidimensional nature of the flow, because we have this, in this case, two-dimensional control volume that we can make sure, for example, that information in a hyperbolic problem only travels downstream. We can take into account the multidimensional flow, unlike in, for example, a dimensionally split method. Of course, there's also, we want the method to be as high order as possible. Want it to be very accurate in smooth flow. We also want it to be monotone. So there's of course, a compromise there. But these are general for any finite volume method. So the main advantage, well, there's three advantages I want to highlight of this particular method, is that you take into account the multidimensional nature of the flow. And in fact, what you're doing, you can view it as a multidimensional Riemann solver, or multidimensional approximate Riemann solver, like the one due to rho, which is important. Very important for planar disk problems. These methods are well balanced in the sense that if you have an atmosphere in hydrostatic equilibrium, then the method will recognize, well, there's no residual, there's no fluctuations, so there's no time evolution. That's a bigger thing than you might think, because many Riemann solver-based codes cannot do that. They will show some evolution away from a hydrostatic equilibrium. Very important for parallelization. The stencil of these methods is very small. So for a second order method, you only need a single triangle. So that's very good for parallelization. So what disadvantage is these methods are complex. They're more complex than perhaps, or at least than I was used to. Just to give you a flavor, so this is one recipe, looks very relatively simple, where you distribute the residual, this is the total residual, but these are all matrices. So, and if you have n equations, these are n by n matrices, we need to diagonalize one, we need to invert one, and we have to do this for every triangle. So diagonalize a 4x4 matrix, invert a 4x4 matrix, and then multiply the two together. So it's expensive. But if you compare that to what you have to do for a normal rectangular grid with a Riemann solver, so if you consider the interaction between these two cells, what you first of all have to do is solve a Riemann problem between the two. But then you go into the multidimensional integration. So you say, well, this Riemann problem, we have to solve 4 transverse Riemann problems as well, because the flow might be in this direction, for example. So this solution will interact with this cell. So there's 4 more Riemann problems to solve. So you solve 5 Riemann problems for every edge in the mesh. So in the end, the speeds are not too different. So they're within a factor of 2. So they're more complex. They're definitely more complex to code, but in terms of speed, they're not too bad. So I've implemented these ideas with the aim of doing, of course, disk-planet interactions. So there's both the mesh generation itself, which is a big pain, and there's the schemes, the hydro itself, the hydro as well. So how does this compare to what more traditional methods? Because that's, of course, we wanted to do at least as good as we did before. So this is a simple, a 2-dimensional standard test Riemann problem. And one thing you may ask, well, if there's a shock, can we handle that on a grid of triangles? And the answer is yes. So there's the shock here. If you zoom in, you see the triangular grid, and you see that the shock is spread over 2 to maybe 3 grid points. So this is as good as you would have for an ordinary dimensionally split or unsplit Riemann solver. So that's good. So here, what I show is a more challenging test. So this is what's called the no problem. So it's an implosion test where initially all the velocities are directed to the center, and what you get is a very strong shock propagating outward. So top row is dimensionally split row scheme. Bottom is the multidimensional upwind, so a multidimensional version of the row solver. And what you see is, in the case of the dimensionally split scheme, you have these preferential directions over x and y. And you see that, well, numerical diffusion along these coordinate axes is just not good enough, not large enough in order to stabilize this very strong shock. So here comes the isotropic diffusion. if you do an unstructured grid, there's no such problem with it because there's no preferential directions, so you don't get these kind of problems. So that's very good. This is a very useful property. This is a property of unstructured, the mesh rather than the method itself. So the multidimensional integration really comes into its own when you consider, for example, the problem of a steady vortex. So this shows the error as a function of mesh size, of grid size, and you can just focus on the solid line, which is the row scheme, the dimensionally split row scheme, which shows nice second-order convergence with mesh size. And the multidimensional upwind method also shows second-order convergence, but the errors are an order of magnitude smaller, which is because they do the multidimensional integration, which is very good to have. So after all of this, let's go back to planets and disks finally. So one way you could do this is to say, well, I have this flexibility in choosing my inner and outer boundaries. So let's cut out a central hole in the mesh. Let's make the outer boundary an outer circle. We have our disk, and off we go. Well, it's possible. It's not a very good idea, because although this looks like a circle from far away, if you zoom in, of course, it's made up of triangles. So it's piecewise linear. So if you then put a hypersonic flow that is circular along this piecewise linear boundary, you get huge artifacts. It's not a good idea. There's ways around that, because you can actually, in principle, you can have curved elements. So you could have a circular boundary, but it makes it really complicated. You can go into moving mesh mode, just having these points rotate at the Keplerian velocity, but again, I'm not a big fan of that. But so the route I chose was, well, let's just do cylindrical coordinates. So let's have our y direction will be phi, our x direction will be log r, so logarithmic, so that you get a good equally sized grid cells for all the radiuses. So this is straightforward, but it's also very straightforward to conserve angular momentum, of course, in cylindrical coordinates, which is extremely important in disks. So I don't have to do anything special for that. So phi is azimuthal. So, and I'm going to skip this. So let's just show some examples finally. So this is very, very recent, basically a progress report. So you have so this is Jupiter in a rather thick disk, just for visualization purposes. So this is already a zoom in, but it's the full 2 pi. This is essentially, for those of you who know, this is the setup of the famous de Valboro test problem, but just with h over r twice the value of that test problem. And what I've instructed the code to do is to say, well, this is the standard de Valboro resolution of a few points per scale height, and I've instructed the code, well, find out where you want a higher resolution based on density gradients, for example, and of course then the spiral shocks are refined to high resolution. You zoom in and you can see what it's refined. There's a factor of 10 in refinement again, but you can the quality of the triangulation gets preserved. So you can, and as far as I've been able to work out, there's no artifacts here, because, even though you go into a coarser mesh on either side. So that's very positive. You can do more interesting things and say, well, so now reducing h over r to the more standard 0.05, but now I've put in a real planet. I've put in a hole in the center, which is actually, in this case, it's the physical size of Jupiter, and just let the mesh sort itself out for that. You can again, these are again refined as well. But if we zoom in on the planet, you get high resolution in the envelope, and as close to the planet itself, you refine, this refinement is basically just because I wanted to have a circle here. So it's very efficient in only this high resolution because I want to resolve what would in the end be the core of the planet. And this is then a dynamic range of about 10,000, and I can do this in an hour on my laptop. So the hope is, and that's you can do you can start to do similar things in 3 dimensions with a proper machine. Right, some concluding remarks. So these methods are not new. So as I've alluded to before, they've been around since the 80s, basically. So this is a review article. But the reason they've never took off, I think, is because it's very hard. Well, there's the investment you have to do in creating unstructured meshes. But also, it's very hard to go beyond first order first order in time, unless you do an implicit time integration, which is a pain. But these schemes are maturing very fast. So there's now explicit schemes, there's higher than second order, and this makes them really a viable alternative to standard Godunov code. So, and I've done various tests, and I've yet to come across a problem where a standard Godunov code will outperform this unstructured mesh code. And I think these meshes offer exciting possibilities to achieve very high resolution. So even in cases where standard AMR is very difficult. So the future, what keeps me awake at night, 3 dimensions. 2 dimensions is it's hard enough to think unstructured, at least for me, and in 3 dimensions it becomes a real pain. So that's definitely something that keeps me awake at night. That's interesting. I'd be interested in doing higher order methods, but also, of course, we need to come back to this has been a very computational talk about the computational challenges, but there's, of course, the challenges in physics as well. Adding all the necessary physics, such as self-gravity. We have to do something properly about the thermodynamics, as we've seen in previous talks as well. So with that, I'll end and take any questions, either computational or about physics. Or thanks very much.
Questions? Yes.
For the very nice review of the methods. I'm just wondering, maybe I have missed it, because at every time step, you also need to move all the nodes. So can you comment on the error property of this step?
So I'm not moving any nodes.
But you have to, so if this is a fixed grid, not moving at all?
So it's not fixed. So what's a good example? So the mesh points in my case, and so they don't have any velocity, or they don't move. But what you do is add points if necessary, and you can also remove points if you don't want them anymore. But they don't have any velocity themselves. And that way, this comes back to the quality of the mesh. That way we can guarantee that the mesh doesn't become distorted. So this is one of the reasons I'm not a big fan of moving these things around. But that's
That's awesome. I was wondering about the last point you made, astrophysics. So magnetic fields and dust. How would you add that?
So magnetic fields is so what shall I say? So as you can imagine, magnetic fields are difficult because if you want, they're difficult in general, but they're even more difficult on a mesh like this because div b equals 0. Well, how are you gonna enforce this? I know there are ways around this, but it's not. I'm not an expert in that. There's ways around this. So dust. So there's no reason why you couldn't do multi-fluid on this mesh.
No, but I meant with particles.
Particles.
Yes.
So
Like how would you do the direct force and back reaction with particles?
so what I would do, I think, so I haven't thought about this. So thinking from the top of my head, what I would do is because of the structures is in place, I would get the particle distribution, create a triangulation out of that, and that will map onto the gas. That'll be difficult, I think, but that would be my first approach to this.
But then you would lose the interest, the thing about the mesh, because you're following the density of the gas, and the density of the gas and particles can be completely different.
I'm not following the density of the gas.
Oh, okay, whatever you're doing with the.
Oh yeah. Oh no, you're absolutely right. So the resolution criteria for gas and dust may be very different.
Yes.
That's true. Yeah. No, that's something that needs to be thought about carefully. Yeah, no, you're absolutely right.
Jonathan?
I just had a quick comment on that question and then a question. So the magnetic field thing, I know people have implemented constrained transport in a repo, so it is possible.
Yeah, that's what I was. So I'm not an expert, but those are the things I was.
It's definitely possible, though. I think a bit of a pain. They're probably easier for you because it's fixed. But the question was, how do you ensure that it stays a Delaunay triangulation when you increase the number of mesh points? Because if you add them randomly and then don't change the vertices of other nodes, do you not end up potentially drawing really weirdly shaped triangles?
No. So the way this mesh is generated is you start from, well, if this is a computational domain, you would start from just two triangles, and then you would add points. But the location of the points is dictated by you want to guarantee the quality.
So maybe I guess maybe my point is more, if you're adding points in the middle of the simulation, do you have to redraw the entire mesh? Or
No, that's fairly local.
Okay. But it's still easy to ensure the quality of the mesh when you.
Yeah. That's what I mean. Okay. You use the same algorithm. It's not. Okay. Removing points is the big headache.
Oh, I see.
Adding points is fine.
Thanks.
So I'll ask first, and then you. I have a question, and then I'll let Jeremy ask his question. What's the prospect on your to-do list of adding what you mentioned, thermodynamics, especially radiation? Because I think you mentioned sort of the critical core mass problem, but I think we've seen throughout this conference and also through published work before that, I think understanding that it's absolutely crucial because all of that seems to be regulated by the ability to cool and hence the opacities that would be included before to basically do the right physics problems. So I'm curious, what are the prospects of that being implemented?
And that's an interesting point, because there's I think most methods that are used on normal rectangular grids, for example, flux limited diffusion, there will be no problem. It's going to be a pain to implement on these. So that's the whole problem with any of this. It's a pain to implement, but it can be done. And what is a long-term goal of me is that, well, this is so for if you want to do something better, like having long characteristics, short characteristics, more realistic radiated transfer. So there's that has been done on these grids for basically reionization simulations. And the interesting thing is that that is what my brother did. So that's my long-term goal, to have a Paardekooper and Paardekooper paper about this. But it's I've been too slow and he's left the field, but still it's my goal. That's the.
I'm very sympathetic to this because it's geometrically natural. Using simplices. triangles in 2 dimensions, tetrahedrons, and those have a lot of advantages if you want to represent. Let's say you were doing, for some reason, as the climate people might, 2-dimensional flow but on a sphere, something topologically non-trivial. You know, in addition to all the advantages you mentioned, you avoid the coordinate singularities at which are inevitable with any sort of regular measure. However, well, 2 questions actually, if that's fair. The aerodynamicists have been using mesh generators for a long time for, you know, to resolve flow over fixed structures, aircraft.
This is where these methods come from.
Okay. So that I just want to make sure you were up to date with whatever they're doing. The other thing is, it's a slightly vague question, but if you're doing disks, it's very important to conserve angular momentum numerically. And if one of your coordinates is azimuth, you know, the coordinate system itself has a symmetry under translation in that coordinate, which helps to preserve angular momentum. Is that an issue with the structured mesh?
No.
I mean, I understand you can have an angular momentum flux, but if you do then give up local conservation of linear momentum?
No, so you can,
It's
well,
a stupid question, but
I've lost my, never mind. So you can, so similar to, so if you're, it's a subtle issue because as it has been for rectangular meshes as well. I mean, there was back in 1998 when Willy Kleib published his paper on the treatment of the Coriolis force in planar disk interaction, where he showed that, well, actually, if you do it the standard naive way, you don't conserve angular momentum because normally these equations are written in terms of the linear momentum, and then you just get the wrong answer. So you'd have to write the equations in terms of the angular momentum, and if you do that, then it's there's no problem. But that's slightly non-trivial in these codes because they are normally written in terms of linear momentum, and there's some special properties. There's subtleties, but that's you can do that relatively easily. Yeah.
Okay, I think with this, let's please thank our speaker again, and then we'll break for lunch.